So thanks everyone for joining today's IGS seminar, which is on the topic of sea ice. Before we start, I want to pay my respects to the traditional original owners of the land on which I join you today. It's the land of the Muvina people, and I pay my respect to those who have passed before us and acknowledge today's Tasmanian Aboriginal people as the custodians of the land. Welcome for IGS, the global seminar. And today we have the honor to welcome Professor Kai Ohshima to present to us. Kai is based at the Institute of Low Temperature Science at the Hokkaido University. He's also a professor at the Arctic Research Center, also in Hokkaido. And he also was working as the program officer with the Japan Society of the Promotion of Science. As many of us know, Kai's areas of specialty are physical oceanography, especially in a high latitude, and obviously the ice-ocean coupled system. I understand Kai's current interest is about the global mapping of sea ice production and obviously the associated exchanges of heat and salt fluxes in the ice-covered polar oceans. He's also interested in coastal polynyas and the processes associated with that, including the bottom water and deep water formation processes around the densification of the water. And obviously the ice-ocean albedo and the feedback and how it results in the sea ice variability are very much of interest. Let me welcome Kai, and we look forward to have you as a single speaker today, so please take your time. And we will have sufficient time for question and answers at the end of the meeting. Over to you, Kai-san.
Okay, thank you very much, Petra. Yeah, please call me Kay. So Kai is like an Australian. No, just kidding. Okay, okay. Kay Ohshima. Okay, can I share the slide?
Yes, please go ahead. And if you can go in presentation mode, that would be great.
Okay, okay. Can you see?
Yes.
Okay.
Yes, it's in presentation mode.
Okay.
Thank you.
Okay. 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 I will start. Okay. But my topic title is Global Transport of Salt, Freshwater, Heat, and Materials by Sea Ice Production and Melt. So this is okay. I will use. Okay. This is the schematics of global transport of salt, freshwater, heat, and material by sea ice. Dense water formed by sea ice production sinks and drives global thermohaline circulation. High ice production occurs in coastal Polynesia, and sea ice production melt redistributes the heat and salt freshwater. And deep or intermediate water change is possibly linked with variation of ice production and melt. We are now creating a global 45-year data set of sea ice production using passive microwave. Sea ice also transport materials such as iron, leading to phytoplankton bloom. Today, I introduce a recent our group activity related with global transport associated with sea ice production and melt. And the contents are the global mapping of sea ice production and efficient polynyal ice production via fragile ice formation, a fate of coastal origin sea ice and its relationship with biological productivity, for the creation of half-century dataset of sea ice production, mapping of ice melt amount, and finally in situ observation in coastal Polynesia in the Okhotsk and Chukchi Sea. Coastal Polynesia are sites of intensive heat loss to the atmosphere and huge ice production occur. Active brine rejection produces dense shell water, sources of Antarctic bottom water or the intermediate water. Heat loss in Polynesia is 1 or 2 orders of magnitude greater than that in the thick ice region. The most effective way of detection of sea ice area and estimation of sea ice production on large scale is satellite using a satellite remote sensing using passive microwave. When we can infer the ice thickness data from microwave, sea ice production can be estimated from the heat budget analysis, assuming that all of the heat loss goes into the ice formation. This is the global mapping of sea ice production by our group derived from the satellite passive microwave. Red and orange color shows the high ice production area. Coastal California is well represented. Number one ice production area in the Southern Ocean is the Ross Ice Shelf California, which is consistent with the Antarctic bottom water formation area. What we find in this ice production map, the second highest production area is the Cape Darnley California. In contrast to the high ice production in the Southern Ocean, the Arctic Ocean, the sea ice production is very limited because the Arctic Ocean is surrounded by the land, and thus a divergent ice motion is greatly suppressed. Okay, this right figure shows the CFC distribution near the bottom. High CFC correspond to the bottom water formation area. In addition to three bottom water formation area, relatively high CFC area exists along the East Antarctic coast. Several studies suggested a bottom water formation occur somewhere around here, but precise formation area has not been identified. High ice production in the Cape Darnley California suggests that this is the unknown fourth Antarctic bottom formation area. Motivated by this ice production mapping about 15 years ago, we made a mooring measurement just off the canyon of Cape Darnley California. This is a time series of the 1 year mooring. This is a temperature time series, and this is a downslope current time series. In accordance to the arrival of cold, dense water, which correspond to the Antarctic bottom water density, the downslope current occurs at the same time. And this downslope current is bottom intensified. So these clearly show that the bottom water is actually formed here. So, this newly developed, discovered bottom water, fourth Antarctic bottom water is termed as Cape Darnley bottom water. The discovery of Cape Darnley bottom water has been followed by a series of studies. However, observation has been limited to the offshore area, and it remains unclear why and how high ice production occur and lead to the bottom water formation. Then we conducted two mooring inside the Cape Darnley California throughout the winter for the first time. These are the 5 month time series of the vertical. This is the key time series. Vertical profile of ADCP backscattering. ADC backscattering can detect particles in the water column. We can find many events of strong backscattering reaching to the nearly 80 meters. During this event, the water is supercooling. And these signals precisely coincide with a high wind condition. Therefore, these signals are considered as underwater fragile ice. It should be noted that fragile ice penetrated to nearly 80 meters, much deeper than previously reported of 20 meters or more. Frequent occurrence of deep fragile event lead to the high CS production. Further, this is a satellite product. Such a fragilized signal can be also detected by the satellite observer. These are the 9-month time series of backscattering, ADC backscattering, and wind speed. And backscattering is highly correlated with wind speed. And penetrating depth of the fragile ice is mostly determined by the wind speed. So underwater fragile ice is mostly controlled by the wind speed. Okay. This is the in-situ video of fragile ice in Terra Nova Bay, Polinia, taken by Dr. Guy Williams during the Piper expedition. These flights indicate fragile ice. What we find in the Cape Dale Polinia from the mooring is that such fragile ice penetrate down to the nearly 100 meters or more during the stormy condition. Okay, from this mooring, we discovered a very, very efficient CS production system. In this region, offshore wind is prevailing. Then huge heat loss occurs. Under this condition, our acoustic measurement detect fragile ice, active fragile ice, which is formed under the turbulent condition. And it penetrated nearly 80 meters or more, which are much deeper than the previous reported. The underwater fragile ice formation could prevent the heat insulating surface cover ice, providing very efficient ice production, causing high salinity dense water, leading to bottom water formation. This high ice production system makes this area bottom water formation site, and in the future, such system should be incorporated in the ocean climate model. These are the 9 months time series of temperature, salinity, and density, and these are schematics, how the sea ice, high ice production lead to the bottom water formation based on these data. In early winter, the dominant fragile ice production causes active brine rejection and deepens the winter mixed layer. In mid-winter, the nearshore water, which has a relatively long residence time in the Polinia area, increases in salinity and density, and this dense shelf water sporadically subducted into the lower layer of the offshore. In late winter, dense shelf water is finally descend down the shelf slope, inducing the compensating onshore wall flow of the modified circumbore deep water. As such, dense shelf water and modified circumbore mix with each other and gradually create new Antarctic bottom water, Cape Dale bottom water. These are the 9 months time series of satellite products, active fragile ratio, and ice production derived from the AMS satellite. these satellite products clearly detect deep active fragile ice. So this ADCP data is a good validation data for the algorithm of satellite algorithm. Okay, this is a map of occurrence rate of deep penetrating fragile ice in the Southern Ocean. We define that the deep penetrating occurrence rate from the AMS algorithm and the wind speed. And this map demonstrates Cape Darley is far dominant deep fragile formation. And this results in the efficient CS production. And then finally, dense photon formation, and finally, bottom water formation. This makes this area the Antarctic bottom formation area. It is also noted that such deep fragile occur also in other polynya. Okay, so deep penetrating fragile ice also potentially play an important role in the transporting particular matter. When the fragile ice reaches the bottom or gets in contact with the least suspended sediment, it could incorporate sediment or micronutrient such as iron into the sea ice, which are then transported to the offshore and finally melted and released when the ice melts, possibly leading the phytoplankton bloom. So therefore, dominant fragile ice formation could potentially contribute to the material cycle and the high biological productivity in the Southern Ocean. In addition, in coastal area in the Southern Ocean, ice shelf water with iron can be also incorporated into the sea ice via ice shelf water. So therefore, the coastal origin sea ice can be a key element for the high biological productivity. Then we're now making the particle tracking experiment of coastal origin sea ice for the Cape Darley area. So initially, deployment of the sea ice flow is based on the sea ice production from our algorithm, Nakata's algorithm, sea ice production. Then we use the sea ice drift data, combined use of AMS product and the wind estimated data using Kimura-san's data. But one notice is one caution exists because the satellite product is not reliable near the coastal region because land contamination occurs. So that's why we combine use of the satellite derived and wind estimate data as the ice drift data. Finally, judgment of the sea ice melt is based on the ice concentration. When ice concentration at the particle position was continuously less than 50% for 5 days, we judge such ice flow is melted. Okay, so this blue lines is from our mooring data, the sea ice drift data. As I mentioned, satellite data is very not reliable near the coast. Satellite drift is shown by the blue one. So we must need some device. So then we, based on the mooring drift data and wind data, we derived wind factor and turning angle. Then we use this turning angle and wind factor and use the ERA5 wind data. Then we estimated the sea ice drift. Red one is a sea ice drift from the wind factor and the turning angle. As such, using a wind estimate data, the sea ice drift without sea ice drift is much well reproduced. Then we use a combined data, one from the ice drift from the Amazon satellite and one from the ice drift data from wind. Okay. Okay, so within a 200 kilometers from the coast, large weight is weighted to the wind closer to the coast, and offshore the Amazon weight is large. So this combined use of the, we use the combined use of the sea ice drift. Okay, these are the results. The upper is combined use of the satellite wind ice drift, and the lower is use of the satellite only. So because satellite ice drift is severely underestimated ice drift, so it doesn't go offshore. So it's not good. So we must use a combined use of the sea ice drift data from satellite and wind. The right panel shows where the ice melt, where the coastal origin ice is melted. Red shows the ice melted area for the average for the 14 years. Okay, so upper is from the satellite and wind tracking and drift tracking, and the lower is satellite only ice drift. So using only satellite data, the offshore transport is severely underestimated. Okay, so that's why we use a combined use of the satellite wind drift data here after. And this light shading area shows the ice melt position. So this is a result of the 14 years ice melt area. So red shows the melted area of coastal origin sea ice. And blue shows the area of the total ice melt, including offshore origin ice melt. So, and the right panel shows the climatology of the chlorophyll concentration. Upper panel is for the December, and the lower panel is the January. And we can find that the high chlorophyll concentration area roughly correspond to the melting area of the coastal origin area. So this suggests that melting of coastal origin sea ice is a key factor of the spring phytoplankton bloom. Okay, we also conducted similar particle tracking experiment of coastal origin sea ice for the entire Southern Ocean. Light blue area shows the melting area of the coastal origin sea ice. Okay. Again. We also conducted particle tracking experiment of sea ice originated from major coastal polynya, distinguished by the different color. Light shading is a melted area from polynya origin sea ice. Okay, this is quite a preliminary result. Okay, then let's move to another topics. One of my colleague, Kashiwasa, is now creating the 45-year data set of CS production. So this is the history of the passive microwave data. So far, SSMI and the AMSA data we can derive CS production, but we don't have algorithm of CNICE algorithm and ice production before the 1992 CIMA period and SSMI period without high frequency channel. I just briefly explain how we can estimate CS production. Okay, first, as a CNICE area, there are two roughly, the CNICE is classified roughly two ice type. One is active fragile, which is formed under turbulent condition, and the other is a thin solid ice, which is formed under calm condition. And using PRGL plot, we can, discriminate active fragile and thin solid ice. Then using a relationship of the PL and ice thickness, we can estimate sea ice thickness. Using this sea ice thickness with heat budget calculation, we can calculate sea ice production. So we need a algorithm discriminating of ice type and thin ice thickness. So such algorithms, Kashiwasa is developing such algorithm. Firstly, AMSA, then SSMI, and finally, very recently, the old passive microwave, he developed SSMI ice type and ice thickness algorithm. That causes, a nearly half-century-year data set of CS production. Okay, this is quite a preliminary one. Preliminary time series of 45-year time series of CS production for the major Antarctic coastal polynya. Blue one is SSMI and SIMR, and orange is high resolution AMSA, and low resolution result is validated by the high resolution MUD product. So this is an example of the nearly 50 years time series of CS production, Ross Sea polynya area of the Antarctic bottom of water formation. And we can also compare with bottom water origin water. So both ice production and density of the bottom water origin water show some trend and decadal variability. So such, we in the future will investigate such relationship. The lower is example of the melt polynya, and as you know, the CS production is abruptly decreased between at 2010. At that time, melt glacier turned collapse. So then the CS production abruptly decreased. So this is a very interesting topic. Interaction between glacier and the sea ice and bottom water. Okay, these are the quite preliminary. Okay, next we move to the melting of sea ice. Okay. Regarding the CS production, there are a series of the quantitative estimating using a satellite microwave. In contrast, very few quantitative studies have been conducted on sea ice melting. Estimation of the sea ice melting is very difficult because of the complex melting processes. Komatsu-san, one of my PhD candidate students, is trying to estimate the ice melt amount from the salinity deficit caused by the ice melt. Just after the sea ice melt, low salinity layer appears on the ocean surface layer, overlying the winter water at the nearly freezing point. The integration of salinity decrease from the winter water salinity should correspond to the total amount of sea ice melt. The Komatsu-san developed the algorithm to detect the top of the winter water, and then using modern nearly 30,000 data, she estimated sea ice melt over the entire Southern Ocean. The red shows the high ice melt area, and the blue shows the low high ice melt area. And based on this estimation, she also made a gridded data set. The ice melt amount corresponds to about 0.84 meter in thickness, which is consistent with the observed ice thickness by ISAT or the aspect. And total freshwater flux by sea ice melt is about 6 times larger than the total glacial melt. So high ice melt occurs at the western side of the three cyclonic gyre. This area is the area that thicker coastal sea ice transported offshore. Okay. Once sea ice melt amount mapping is established, when we combine with when we combine the CS production by the previous satellite product, then we can mapping net freshwater flux by CS production and melt. This is a very result of the combination of the CS production and CS melting together. This is probably the really fast mapping of the net freshwater flux by the sea ice, only from the observation. Red shows the freshwater flux area, and green or blue shows the salt flux area. And very high salt flux area occur in the coastal plain, and relatively low freshwater flux area offshore. And right panel shows the freshwater flux by latitude associated with the sea ice production melt. And salt flux change at a latitude of 62 degrees south. Independently, my colleague, one of my colleagues, Dr. Nihashi, is now developing an algorithm of sea ice melt amount from satellite passive microwave and heat budget. I don't introduce the method in detail, but he used the ice concentration, ice motion from satellite, and heat budget calculation. This is a tentative result of the estimated ice melt amount, accumulation of the ice melt amount. There are several relatively high ice melt large area. And we compare his satellite result and Komatsu's result based on the salinity deficit of the hydrographic profile. And surprisingly, both ice melt distribution well correspond to each other. High ice melt area occur in the same place. So we are thinking that this satellite algorithm, ice melt amount, may work well, but we still underway for the developing. But for making that algorithm, this Komatsu's data set is a very, very good validation data. Okay, finally, I will finally introduce the modeling result of the Seaborg and Chakchi Sea briefly. And this is the result of the mooring observation in the Seaborg. And we deployed two bottom-mounted ADCP data. And we can find fragile ice and also upward dispersion of sediment. Then interaction between fragile ice and sediment occur. So we call suspension freezing. Then such process is a high, proposed process. How the iron or sediment is incorporated into sea ice. Okay, similar observation was also made in the Chakchi coastal sea. We have continuously made a mooring observation, collaborated with the University of Alaska, and this is a result of the time series. This is also the ADC backscattering. So windy condition, fragile underwater fragile ice occur, and high bottom water condition, sediment is dispersed upward, and water is supercooling. Then underwater fragile ice sediment interaction occur, and suspension freezing occur. This also proposes the suspension freezing is a process how the sea ice incorporates sediment or iron into the sea ice. Okay, this is the final slide. Thank you very much for their attention. Thank you.
Thank you, Kay.
Okay.
Very. I couldn't remember how you asked me to pronounce it. Is Kay correct?
Hey, yeah. Now.
Thank you.
No,
Okay.
correct.
Okay, thank you very much for this marvelous and really intense presentation. So I open it up to the audience, and there's only a smallish number of online participants. So please unmute yourself and feed your curiosity. Are there any questions? And actually, while people get up, I was just there's so much, so thanks for covering that. I was wondering, you presented the difference roughly halfway through the presentation of the wind-driven versus the satellite-detected offshore movement, and then east-west, westward movement. So when you blended that product, did you normalize, or how did you create a combined product, which I understood you were doing, and how have you validated it against any measurements?
Mm-hmm. Okay.
Yes, we can see the shared screen again. Thank you.
Okay. Okay. So you have several mooring data, ADCP mooring data. So ADCP data observed sea ice drift. So we, derived wind factor and turning angle based on the several ADCP ice drift data. Then we apply using based on the ERA5 wind data. Then we calculate sea ice drift. Then in this case, sea ice drift is well produced by the using a wind factor and turning angle. This is the only validation right now. So so I think it's not so easy to have an further validation. So our plan is to use the sensitivity of the sensitivity to the wind factor and turning angle. Then we try several experiments how such a how the tracking is sensitive to the wind factor or turning angle. And
Yep.
okay, so this weighting function is a tentative one. So it is also check how we made an appropriate weighting. So this is also another problem. So this is still underway. Okay.
And you apply this weighting function, the same weighting function around the different regions of Antarctica.
Yes, the same tentatively the same weighting function. So probably this method is probably relatively correct for the region of the Cape Dunley area, but we are not sure such value or such method is also appropriate for the other area. So that's challenging in the future work. Okay.
Yes. Yeah, I was wondering how you deal with areas that have
Okay,
lower
the same.
gravitational
Yeah.
force.
The same wind factor and same turning angle, same wind function. Okay.
Sorry, I muted myself. Thank you very much. I see a hand up. I believe Roland, would you like to ask a question?
Yeah. So, Kay, thank you for a fantastic survey of a tremendous amount of work. I was particularly interested in the first portion of your talk about frazzle, partly because here in Hobart just this week we had a seminar about sea ice physical and biogeochemical processes, and this was from Letizia Tedesco from Finland, and she showed some much rarer than your data, I suppose. She showed some profiles of the texture of sea ice in sea ice cores from the Weddell Sea with this granular facies from deposition of frazzle ice, and the sea ice ocean modeling people in the room were suddenly very agitated because this frazzle mechanism basically isn't actually in any of their models at all. So I was wondering, are you able to estimate, you concentrated on polynyas as these very high production regions. Would you be able to estimate the total fraction of sea ice that might actually have a frazzle origin?
Mm-hmm. Okay, so it's not easy to from the in-situ observation, but we only estimate ice production from the active fragile area or the sea-solid area from the satellite data. So in the case of the Cape Leporini, so the CS production is CS production in the active fragile ice is a bit larger than the CS production in the sea-solid ice area. So we can only estimate from the based on the satellite data, but it is not so easy to estimate fragile ice ratio in the in situ observation. So one way is to collect sea ice sample and check the sea ice crystal fragile ice, granular ice, or the conjugated ice or like that. But we have not yet such thing.
Do you think that a lot of this deep frazzle ice might actually get carried under that solid ice and deposited there as well as rising to the surface in the Polinium?
I suppose so. So fragile ice formation is much important than previously thought. I think so. That's a main message from our mooring observation. So,
Thank you.
Thank you very much.
Okay, thank you, Roland. Just to add, I was wondering if you obviously would have taken some sea ice cores during your expeditions in the vicinity, and there was no evidence of intermittent or basal frazzle ice in the ice core stratification.
Pardon me?
When you have an expedition, have you had the opportunity to take some sea ice cores in the downstream region, and have you looked in the stratigraphy if there was interstitial or basal inclusion of those frazzle crystals?
You mean collecting the sea ice sampling?
Yeah, if you take a sea ice core and take like a 6 section or so, and you look at the crystal shape and the crystal structure, have you been able to identify layers of frazzle ice in the bottom of the ice or in the middle of the ice core?
Okay, so we have not yet such ice sampling in the Cape Leporini, but recently the Japanese Japanese Antarctic expedition project is focused on the offshore of the Totten Glacier. So one of my previous PhD student, Dr. Ito is the major leader of CS collecting. So he made a lot of ice sample offshore the Totten area. So that such ice sampling may give information how the fragile ice formation or granular ice formation is dominant or not in the coastal area. So
yeah.
Yeah.
So I'm looking at fast ice cores from Mawson and Davis for most years, and I've seen frazzle incorporation in the 1990s in the Davis ice cores, but nothing at Mawson. I assume it's too far in on the shallow part of the shelf, but that would be an interesting study to do. All right. Thanks, Roland, for your question. May I invite any other questions that people might have of Kay today, please?
Excuse me.
Sorry, yes. Please go.
Go ahead.
Yeah,
Go
Shin,
ahead,
please go ahead.
Okay, then thank you. I'm Shin Sugiyama, a colleague of Kei, and listening to the talk in the same building. But thank you very much for the beautiful and very intensive multidisciplinary research work around Antarctica. And let me take this opportunity to ask very amateur sea ice question. What do you see about this recent decline of sea ice in the Antarctica, not in Arctic? So we are seeing clear change in this trend. And I'm frequently asked by my friends and people what is going on and what is the future prospect of this change in sea ice in the south. If you have any suggestion for me how to answer these questions to my friends.
Okay. Okay, thank you very much for your question. That topic is not directly related with my today's topic, but
Excuse
actually,
me for this.
Yeah. But actually, that topic is one of the focus of my very current, study. So I co-work with Dr. Nihashi, and so there are several proposals, such as from the Australian guy mentioned, proposed that ocean warming causes such, decline. But Dr. Nihashi and I think that one of the factors abrupt decline is the ice-ocean albedo feedback system. Ice-ocean albedo feedback system. So once sea ice is divergent, so many open water fraction occur. So such open water fraction easily absorbs solar radiation. That then solar radiation heat the warm ocean heated by the solar radiation melt sea ice. Actually, most of the sea ice in the Antarctic sea ice is melted by the ocean heating. Ocean was heated by the solar radiation. So just before the record low minimum in last February, November, December is a period of the active ice divergent period. Then a lot of open water occur. Then a large solar radiation is absorbed. Then such heat is melt sea ice. That's our present tentative scenario. So we are now investing such scenario is really well explained the record minimum. So not so. Of course, this is one proposal. There are several candidates for such a sudden decrease. I think it's underway. Thank you. Thank you very much for that.
Thank you very much. Albedo feedback I frequently hear in the Arctic, but now I learned it is also happening in Antarctica.
Yeah.
Thank you very much, Kei. Thanks.
Thank you.
Thank you for your question, Chin. Ralph, do you still have a question?
Yes, hello. Ralph Greve,
Hello.
also at the Institute of Low Temperature Science, same building as Kei and Chin. I'd just like to know, you said you're planning to make this data set available, right?
Pardon me, can I see the volume is small, so please say it again. Okay.
Is it now better?
Okay, yeah.
Okay, I'd just like to ask about this data set you're planning to release. Do you already have some concrete plans how to manage that? So when roughly will it appear and where will it be hosted? Which format?
You mean the data set of the CS production?
Yes, sure.
Yes, that's a very important question. So the data which I present today is quite a preliminary. So once such data is validated and published a paper, we plan to the data set is open, of course, that's very important. Of course, some of the data set is already open in my homepage, in our group's homepage, already open. So, the open data will increase day by day in the future. Thank you for your pushing of such publicity. Okay, thank you.
The point is also, it's quite important to have a bit of a management for such products. Yeah, also let's say future updates and things like that. So it's definitely worth thinking a bit about this. Yeah.
Actually, one of our product is now the research product of JAXA. Research product of JAXA. So JAXA product is open. So one of our, some of our products is already open through the JAXA homepage. Okay.
Okay. Thank you.
Thank you.
Thank you very much. Toshiyuki, please.
Hello, Kate.
Hello.
So my question is very primitive, and maybe this is a kind of a future problem. And you said that deep fragile ice plays very, very important role in deep water formation, but has not been taken into account in the global model. And my question, number one, is that, do you have, hello?
Hello, yeah. Telephone call, okay, sorry.
Yeah. Do you have some quantitative assessment how much deep water formation is promoted by taking into account these deep fragile ice processes?
Okay, so yeah, that's, I think the final goal is how such process is incorporated into the ice ocean couple model or the climate model.
Yeah, that's number two. Number two, a question. This is a very small scale processes. So I wonder how this important process can be incorporated into a global ocean or climate model. So number two question is, do you have some strategy and take into account of this important process, but has not been taken into account so far? I think this is a very important processes for global ocean circulation or climate model. So quantitative assessment and strategy incorporating into a global model, some parameterization, or you estimate each area such as deep fragile ice effects independent. What kind of a strategy do you have in the future?
Yeah, that is the final goal. So yeah, but there are several steps for that. So firstly, so probably this is the final goal. Also, it's a very, very difficult question. So so firstly, we must compare the satellite result, satellite product and the mooring result. That's the first step. And small scale to the satellite footprint scale, combined. Then satellite product and larger scale is made. So probably mooring, satellite, then combine how the incorporate into the models. That is a flow of the investigation, but I don't have a specific idea how it will be done. So probably we must deep discussion with modeler, in near future. So sorry, that's my answer.
Okay, thank you very much.
Thank you very much for your question, Toshi. I guess all the questions really highlight how important this research topic is and how it connects quite in a lot of other disciplines. I have lots of questions, including, glacial meltwater runoff and how that would affect it, and obviously changes in the system as we expect them for the future would then reduce or pump up the importance of certain processes. So really interesting area. I thank you very much. I would like to thank you very much for your presentation and invite all the others to give us a thumb up on the online. And I remind people to put themselves forward if they want to present at the IGS seminar series, either in the CI's compartment or in a more general section. Please contact the IGS seminar organizers. Thank you everyone for attending. Thank you very much, Kay.
Thank you very much, Petra, for your arrangement, and thank you very much for the audience to join my seminar. Thank you very much.
Yeah, very important talk.
Thank you, Hida-san.
Thank you.
Thank you.
Thank you. Thank you.